This is our first lecture regarding the course EENG 301. We'll talk about Ohm's law and the connections of resistors. We have two connections, series and parallel. First, if we apply a voltage source across a resistor R, then there will be a current passing through R, dictated by Ohm's law. So E is the voltage across R. The current will pass through voltage R of value I, and if we draw the relationship between the current and the voltage, we'll find it's linear. The slope of that relationship is equal to R, E over I equal to R. This is basically voltage current relationship, which is Ohm's law. Notice that the current in the resistor shall flow from the higher voltage node to the lower voltage node. So this is plus, this is minus, means this node is higher than the this node by value V. So this V here, volts, how many volts, means that this node is higher than this node by that much voltage. And the current will flow from the higher voltage node to the lower voltage node. So this is basically Ohm's law, and this is the first fundamental law in electric circuits. Now we'll go to the other two laws of electric circuits. The first one calls Kirchhoff's voltage law. Kirchhoff's voltage law, or KVL. KVL basically it says that if we have a closed loop, in that closed loops we have elements, resistors and voltage sources, for example. So the sum of all voltage across these elements should sum to 0. So if we assume that the loop is clockwise, which means the clockwise, we assume it as a positive direction, then the anti-clockwise is assumed to be negative. So the sum of all voltage is 0. In this closed loop, we have three voltage sources, E1, E2, and E3. E1, this is a plus, this is minus, means this is the direction of the voltage source. So it is in the same direction of the positive, it is of the clockwise direction. So E1, we should assign a positive value to it. If you watch E2, E2 is in the opposite direction. This is minus, this is plus. So this is the direction of E2. It is in the opposite direction of the loop. So we assign a negative sign for it. Similarly, E3 has a sign opposite to the loop. So we assign also a negative sign to E3. That's when we add them, so plus E1, minus E2, minus E3. Then across resistor R1, we have a voltage, we call it V1, plus minus. Why plus minus? Because the current is in this direction, which means it passes through R1 from the positive or the higher voltage node to the lower voltage node. So this is V1 across R1, it means this is plus, this is minus. So this is the direction of V1, which is in the opposite direction of the clockwise. So it is in the anti-clockwise direction. So I apply minus V1 to it. Similarly, minus V2 and minus 3 and minus V4. Okay? So that's the way how we apply KVL to elements in a closed loop. So this is second basic law of electric circuits. We had Ohm's law, we had KVL, and the third basic law in electric circuits is KCL, or Kirchhoff's current law, which applies to a node. So if we have a node and many currents are injected into this node, so the sum of all currents injected to the node should be equal to 0, or should equal to 0. So sum of all currents injected into the node should equal to 0. So if we assume that a current goes into the node, which enters the node, we assume it as positive, which means the current comes out of the node or leaves the node, we assume it as negative. In this example, I1 enters the node, I2 enters the node, I3 enters the node, I6 enters the node, I5 enters the node, so we assign positive to them, while I4 leaves the node, we assign a negative sign to it. So I1 plus I2 plus I3 minus I4 plus I5 plus I6 equal to 0. So this is KCL, or Kirchhoff's current law. Now we have Ohm's law, we have KVL, and we have KCL. We'll apply these three laws to electric circuits and see how we proceed. Example of a series circuit. This is a series circuit. A series circuit consisting of 3 resistors. One is 5 ohms, one is 10 ohms, and one is 30 ohms. Also, we have 2 voltage sources. One is 12 volts plus minus, and the other is 100 volts plus minus. So we can use KVL to determine the currents I. I flows in all of them. It flows in the 5 ohms, it flows in the 10 ohms, and it flows in the 30 ohms, it flows into the 12, and it flows also into the 100 voltage source. So we can use KVL to determine I. We make a loop clockwise through. Assume that the clockwise loop is I, so it is in the same direction as the current passing through all of them. So this source, the 12 volt source, in the same direction, so we assign a plus to it. The voltage across the 5 ohms resistors is in the opposite direction, so it is minus 5 V5 ohms, minus 10 V10 ohms. In the 100 volts, minus a plus, so it is in the opposite direction, so it's minus 100, minus 30. You watch, the current flows in this direction here, means plus, minus, so this is the B30 ohms, okay? So, the voltage across 5 ohms according to Ohm's law is 5I. Similarly, the voltage across the 10 ohms is 10I, and across the 30 ohms is 30 times I. Remember, always when you have a resistor R and the current passes like this I, then this is plus minus V. So the current flows from plus to minus. Then you say V equal RI. This is the correct way. Okay. So from this we can calculate the current will be minus 88 divided by 45. So you obtained a negative value of the current. It doesn't matter. We assume the current in this direction. It turns out to be negative. It means the actual current will be in the opposite direction. So this is an application of KVL. Let's apply KCL to this node N, where we have a current 5 amps injected into the node, another current 3 amps, injected also into the node, and a current 2 amps leaving the node. And we have a current leaving the node of unknown value I want to calculate it. So apply KCL to node L. 5 is injected into, so it is plus 5, plus 3 because it's injected, minus 2 because 2 is leaving, minus I because I also is leaving the node. So I will be 6 amps. Let's go to the series and parallel connections of electric circuits. So this is a series circuit consisting of R1, R2, Rx, Rn, and all together are connected to a voltage source A. A current will flow into all of them. The current flowing into resistor R1 is I1, into resistor R2, I2, into resistor Rn, Rn. But I1 and I2, all of them are the same. So the current flowing in all resistors, all elements, resistors and voltage sources is the same current. So we say it is a series circuit. So we can transform this circuit to a simple circuit having a single resistance R total. The same current passing through all these resistors passes through R total with the same voltage. So we call this an equivalent circuit of the original circuit. So this is equivalent circuit. Okay. So we can simplify this circuit with a single resistor. The value of this resistor, we'll see how we obtain it by applying KVL. If we apply KVL, A minus V1 minus V2 minus all voltage equals 0. Why? Because A is in the same direction. We assign the loop like this here. This is the loop I. So A in the same direction of the loop. However, the voltages across the resistors are in the opposite direction, plus minus. So it is in the opposite direction, which means that E is equal to the sum of the voltage across the resistors. So it is R1, I1, that's V1, R2, I2, that is V2, and so on. But I1, I2, In is the same as I, which means that we have the sum of all resistors times I. So this is equal E equal R total times I, where R total is the sum of all resistors in series. Then from this we obtain a useful rule. We name it voltage divider rule. So this is the voltage divider rule. Voltage divider rule, which basically how we determine a voltage across resistor Rx, knowing A and total resistance. So basically Vx equal Rx times I, but I is equal E divided by R total. So Vx is equal Rx divided by R total times E. Okay? Let's go to parallel circuits. And see the parallel circuits. In parallel circuits, we connect all elements, all resistors between two nodes. This is one single node, and this is another node. In mechanical engineering, this is similar to a header or manifold, and this is another header or manifold. So all links here are connected between these two nodes. So all elements are connected to a common voltage source. So the voltage across R1 is the same as the voltage across Rx, the same as the voltage across Vn. So the voltage between these two nodes is the same for all elements, which means that V1 and V2 and Vn are the same. If we apply KCL to this node here, then we get I total minus I1 minus I2 minus In equal to 0, which means that I total is equal to the sum of the currents passing through all these resistors. Now we transform this circuit to an equivalent circuit. This is an equivalent circuit. Okay. And that equivalent circuit, we apply on this equivalent circuit the same voltage here, and we obtain the same current in here. So what is I total here? Is basically V divided by R total. That's Ohm's law. So I total is V divided by R total. And I total is equal to the sum of all these currents. And I1 is V over R1, Ix V over Rx, and so on. So I total is the sum of all currents, which means that V total equal over R total is equal I1, which is V total over R1, I2, which is V total over R2. So we take V total as a common variable, so we get 1 over R, which means that 1 over R total equal 1 over R1 plus 1 over R2 plus 1 over Rx plus 1 over Rn. So the reciprocal of the resistors, the total resistance is equal to the individual sum of their reciprocals. And notice that 1 over R, we name it as G. G, which means conductance. Okay, the inverse of a resistance, and its unit is Siemens, S. Which means that the total conductance of the circuit is equal to the sum of conductances of all resistors. Okay. Also, what we have here for parallel circuits, similar to the series circuits, we had there a voltage divider rule. Here we have a current divider rule, CDR. Basically, if we have parallel combination of resistors, then we can find a current in an element, say Rx, what is Ix, from a knowledge of our parallel combination of resistors and the total current. Basically, Ix equal voltage divided by Rx. What is the voltage? The voltage is R total times I total. So it is Ix is equal R total divided by Rx times I total, where R total is the parallel combination of all these resistors, and we use the two parallel lines to symbolize parallel connection. So it says R1 parallel with R2, parallel with Rx, parallel with Rn. And if we apply this as a special case to two resistors, R1 and R2, we can consider this an easy way of finding R total of R1 and R2. So 1 over R total equal 1 over R1 plus 1 over R2, which means that is R1 plus R2 divided by R1, R2. Which means that R total is equal R1 times R2 divided by R1 plus R2. So if we have two resistors in parallel, then the parallel combination of them is the multiplication of both resistors divided by the sum of the two resistors. And if we apply currents divider rule for I1, I2 is simply I1 is R total, which is the parallel combinations between R1 and R2 divided by R1, because we are calculating I1. Similarly for I2, we do the same. So if we replace R1 parallel with R2 by R1, R2 divided by R1 plus R2, we obtain I1 equal R2 divided by R1 plus R2 times I total. This is it. So basically, if we want to find I1, we take R2 and divide it by R1 plus R2. If we want to calculate I2, we take R1 divided by R1 plus R2 times I total. Okay? Now let's look at the series parallel circuits, which means that we have combination of connections, series and parallel. This example, we have two resistors, 60 ohms and 30 ohms are connected both in parallel, and then connected in series with 80 ohms to a voltage source of 100 volts. Fine. We want to determine R total. When we say R total, what we mean by R total? Seen by the source. What is the resistance of the circuit that is seen by this source, by the voltage source? This is R total. And we want to find also I total. I total usually we call supply current. Supply current. Why supply current? Because this current is supplied by the source. We want to find it. And also we want to find I1 and I2. I1, the current passing through the resistors, the 60 ohm resistors, while I2 is the current passing through the 30 ohms resistor. So usually when we try to find, to analyze circuits, we start from the far end. That's the far end of the circuit. And this is the beginning of the circuit. This is the far end. So we start from the far end. We see that the 30 ohms and the 60 ohms are connected in parallel. So we find Rx, the parallel combination of R1 and R2, which is 60, parallel with 30, which is 60 times 30 divided by 60 plus 30, you will get 20 ohms. So the parallel combination of 30 and the 60 is 20 ohms. Then this is connecting, this is two nodes, the same two nodes here. So this represents Rx here, then it's connected to the source through an 80 resistor. So Rx we have calculated 20 ohms and the 80 are in series. So we add them, 20 plus 80 will give you 100. That is the total resistance seen by the source. So the source sees a resistor of 100 ohm and will supply a current to it, which is equal this 100 divided by this 100. So we will get 1 ohms. That's the supply current. Now this supply current will be divided into two currents, I1 and I2. And we can determine I1 and I2 using current divider rule. I1, apply the current divider rule. I1 is the current in the 60 ohms resistor. So Rx is 60 ohms resistors. R total is not this R total, the 100 ohm. No. If you apply the current divider rule, the R total in the current divider rule is the parallel combinations of the mentioned resistors. So we are talking about a parallel connection between R1 and R2, between the 30 and 60, and we want to apply the current divider rule for both resistors. So we take the parallel R total, for the sake of current divider rule, is the parallel combinations of 30 and 60, which is 30 parallel to 60, which is 20 ohms. So I1 will be 20 divided by 60 times I total, which is 1, so it will be 1/3. Similarly, for I2, we take 30 ohms parallel with 60, which is 20, divided by Rx, which is R2, which is 30 ohms, so we get 2/3. So you see that the current, the 2/3, passes through the 30 ohms, while the 1/3 passes through the 60 ohms. So the lower resistance will cause a higher current into it. Okay? So this is basically the basics for this lecture. So from this lecture, you know that this is the basics. We have three basic laws: Ohm's law, KVL, which is Kirchhoff's voltage law, and KCL, Kirchhoff's current law. And from these three laws, we know how to calculate series resistance, parallel resistance, and a combination of series and parallel resistors. So in the second short over video, I will send you another short video about some few examples of series parallel combinations, and we'll add to them also capacitors and inductors, and I'll show you how you calculate the currents in the inductors and the voltage across capacitors, and how we calculate the charge, how we calculate the stored energy, and how we calculate the magnetic flux. And you remember the first few videos we are talking about direct current circuits or sources, so it's DC. We are not talking about IC in this first few videos. We're talking about DC currents. Okay, so we'll talk to you later.